Welcome you all today for the lecture on operation and control of AC microgrid part 2, in which we will once again talk about what is the importance of microgrid control, hierarchical controls, intelligent control techniques, and finally the overview of microgrid controls. Now, the major key control variables in a microgrid is voltage, frequency, reactive power and real power. So, as a whole 4 variables: real power, reactive power, frequency and voltage decides the overall key control variables of a microgrid. Now, voltage and frequency regulation under any operating condition is must. Active and reactive power control to achieve proper power sharing under grid connected as well as in the islanded mode of operation is possible through microgrid controls. A seamless transition from grid connected to an isolated mode and vice versa. Participation in energy market with optimized production of micro sources. Uninterrupted supply to critical load such as schools, hospitals and other essential services possible. Capability of black starts in case of grid failure. Optimized operating cost of production and power exchanges within the utility grid. Now, let us move into hierarchical control. Now, in case of hierarchical control, we can see the distribution network, which is my main grid and which has been connected to the global controller. And now, if you do imagine that I have or we have connected microgrids at different buses of the distribution network, and there could be as many as n number of microgrid could be connected to my distribution system. Considering this is by microgrid 1, microgrid 2, microgrid n. Now, how all those microgrids can experience a common control goal, and in case of a single microgrid, we will first experience the local control followed by secondary control and hence central and emergency control. And this kind of scenario must be repeated at each and every level for the local control, so that all the microgrids can operate effectively, those have been connected to my distribution system. Now, getting deeper into this, now this is my local control setup between microgrid, and we do have secondary control at each level. And now the distribution network owner or operator that links to my microgrid 1, 2 and n, and each microgrid will experience those secondary control as well as local controllers. And the microgrid control connected to my distribution system, and the signal may come from each and every individual microgrid controller from different microgrid through DNO. Now, what is distribution network operator or owner? Now, the distribution management system or the distribution network operator has the responsibility to manage the operation of medium voltage and low voltage area in which more than one microgrid is connected. Now, if you have a single microgrid, certainly there is a one-to-one communication, but if you have multiple microgrid, we have to utilize all the microgrids effectively, so that the DNO can nicely manage all the microgrids effectively. Now, in case of for each microgrid, there is a central controller known as MGCC that interface between the DMS, distribution management system or distribution network operator, and the microgrid So, that means the microgrid and the DNO has been connected through my microgrid central controller. Now, to balance the market and the local need, because the market is expected to have lot of profit, whereas the customers at this consumers end expect high heat demand, efficiency and good power supply. So, there is a local need as well as there is a market need, and those two need to be matched simultaneously. Now, in case of local hierarchical control, the local control includes fundamental control hardware, comprises distributed generation internal voltage and current control loops. It maintains distribution generators stability by measuring and controlling the local signals, basically works in the decentralized fashion. Now, the main usage of local controllers is to control distributed generators to operate in normal operation. The local controllers for a distributed generator that operates as a voltage controller, voltage source converter, that is VSC, where the voltage reference is provided by conventional droop controllers. This controller feeds the current signal as a feed forward term via a transfer function, that is virtual impedance, that will be introduced in the later of this course. The proportional integral PI controllers are widely used to the design of the control loops in the local control level. Now, let us try to understand the concept of droop control. For example, the moment we say 5% droop means that a 5% deviation in normal frequency causes 100% change in my output power. The interconnected generating units with different droop characteristics can jointly track the load change to restore the nominal system frequency. For an example, if you consider the droop characteristic for inverter based DG with inductive line impedance VQ droop, if it is my PF characteristic, this is my P and F. Now, what it says that for a change in frequency from this point to this point may change the power from this point to this point. Now, this characteristic may be suitable for generator 1. Similarly, we can have another droop characteristic for generator 2. For the same frequency change, the power may change, but the change in power for the generator 2 is different than the generator 1. Two generating units are operating at unique nominal frequency with different output powers. Any change in the network load causes the unit to decrease their speed and the governors increase the output until they reach a new common operating frequency. So, we have to keep on changing until they both get the new common operating frequency. The amount of produced power by each generating unit to compensate the network load change depends on the unit's droop characteristic. Droop control. Now, if I consider one more droop characteristic between Q and V, you can clearly see the voltage, if it is dropped by this magnitude, then my Q is reduced by delta Q magnitude, or indirectly if you increase the Q by delta Q1, the voltage may come from this point to this point. So, there is a strong relationship between V as well as Q. A voltage variation So, V0 leads to Q10. When voltage drop to V, now the Q become Q1. So, droop characteristic for inverter based DGs with inductive line impedance VQ drop. Now, we may have different V as well as Q characteristic for other generators. So, as though the generators are different, the V and Q characteristic, droop characteristic become different. So, for a given voltage change, you will experience different reactive power changes. Now, the inductive conventional grid droop equation, we can obtain that V minus V naught, which is K times Q minus Q naught with a negative sign, as you have seen, or otherwise I can say V minus V naught is KQ times Q minus Q naught, and whereas for frequency it is my P minus P naught. So, we can see there is a strong relation between V and Q and F versus P, and the change can be plotted as PF or QB droop characteristics. Droop control drawbacks. What are the major problems or the limitations of a droop control applications? A small mismatch in the grid impedance estimation could result in an inefficient power sharing among the droop controller distributed generators. It is unsuitable for nonlinear and single phase load as the harmonic current sharing is not taken into account. Poor voltage regulation of critical loads with the application of reactive power. So, the droop control approaches further improved with different approaches. The first one is virtual impedance method, adaptive droop control, angle droop control, virtual frame transformation, virtual inertia based droop control. So, now concentrate on virtual impedance based droop control. The performance of a droop control system in a microgrid is highly dependent on the grid impedance parameters, that is R by X index, especially in the general case where the grid is both inductive and resistive. Using a large inductor between the power converter and the AC bus to make an inductive line impedance is one of the solution for improving the power sharing in droop control. A simple but effective solution is that updating the power converter control loop by virtually emulating the effect of an inductive element in the link impedance. This concept is known as virtual impedance and has been successfully implemented for regulating the power sharing among parallelized inverters and limiting overcurrent under grid disturbances. Improved droop methods. Now, in case of adaptive droop control, a modified voltage droop is proposed which improves voltage regulation by eliminating the connecting impedances between VSC and point of voltage control. In this method, the voltage drop across the connecting impedances between VSC and common AC bus are included in the conventional QV droop control. Angle droop control. Angle droop control has significantly low frequency deviation compared to the frequency droop control. The phase angle measurement of the output voltage of the VSC can be used from low bandwidth GPS based communication techniques. Now, in case of virtual frame transformation approach uses a linear orthogonal transformation matrix to refer the active and reactive power flow equations to a new reference frame. Virtual inertia based droop control, the purpose of adding inertia to the system is to avoid unwanted triggering of circuit breakers due to under frequency and over frequency relay malfunctions. Now, the secondary hierarchical control, the secondary control provides power sharing as a communication based method for parallel configuration of DGs and compensate the voltage and frequency deviations caused by the load variation and local control operation. Secondary control as second layer control loop, as we have seen in the previous diagrams, complement the task of inner control loops to improve the power quality inside microgrids and to enhance the system performances. They are closely working with local and central control groups. Secondary control operates on a slower time scale compared to the local control. Now, the central hierarchical control facilitate microgrid supervision activities, and its role is particularly important in the islanded mode of operation. It operates as a microgrid energy management system and monitors the microgrid local and secondary controllers. It is also responsible for islanding detection and connection disconnection to or from the main grid, as well as emergency control and overall protection schemes. It is centralized and mainly based on communication. Secondary, central, emergency control distributed types. Let us discuss on multi-agent based techniques. The primary element of the multi-agent system based technique is an agent which can be physically or virtual entity situated in an environment and capable of autonomously reaching to changes in that environment. A multi-agent system has two or more agents with its intelligence being characterized by its reaction to the environment, proactiveness, goal oriented action, and social ability, that is communication based agents. Moving into model predictive control techniques, model predictive control, so called MPC technique, is a futuristic approach where an optimization problem is solved based on demand and generation forecast and prediction of dependent variables are carried out. So, here we imagine a step ahead. It is advantageous as it solves multivariable optimization problems using forecast with feedback mechanism and handling power system constraints as well. Consensus based control techniques. In consensus based distributed control, a distribution optimization problem is solved to arrive at a converged solution for all the distributed energy resources present in the system or connected to our microgrid. Now, in case of a centralized approach, in the centralized approach, the microgrid central controller, that is MGCC, provides power set point to my local controllers LC for their operation. So, you have to create the local controller points, and those have been created by the MGCC so that each local generation points can behave based on the instruction available to me from the MGCC. Assume in a small microgrid, and if you have around 3 to 4 different sources, and those sources will have my 3 to 4 local controllers, and with a single MGCC, the LC can communicate with my MGCC and take action at the local end as desired by the MGCC. The LC includes the controller at micro source as well as at load. Here, bidirectional communication between MGCC and LC is necessary for a reliable and efficient operation of the microgrid. However, a single point of failure can disturb the complete electricity services. The primary benefit of the centralized control strategy is online optimization of input parameters like operating set points, constraints, network parameters, as well as taking care of forecasting informations. Global control manages the power flow between the given microgrid, other interconnecting microgrids and the main grid. Now, the global hierarchical control is a step above, where it manages the power flow between the given microgrid interconnecting to other microgrids. The global control receives power reference from the distribution management system, that is DMS, and processes the error between actual and the reference values. It facilitates an economically optimal operation. It is the slowest control in the hierarchy. The compensators are used to process the error between the active and reactive power at each level injected to the utility with their corresponding references. Certainly, it is a centralized control. This level is working in the distribution network area outside the microgrids. Finally, we get into intelligent control techniques, because as we all know, the control schemes are never ending, and for the microgrid the complexity is extremely high, and we have to evolve with new techniques to achieve a target oriented error or the problem associated with the existing technique. So, currently many intelligence techniques have been evolved. Intelligent techniques based control has a wide research scope in the power system applications with power electronics. The first one is my fuzzy controller, adaptive neural network controller, genetic algorithm based controller, particle swarm optimization based controller, adaptive neurofuzzy inference systems, multi-agent based controllers. And to conclude today's lecture, let us understand the overview of AC microgrid control. Now, to focus in this case in the control mechanism, as we have seen that at each and every level the droop control is very commonly and widely used, but it has certain limitation, though it is robust. So, it has been evolved over a period of time. But looking into the microgrid control schemes considered to be one of the most important, because please try to understand, you do have a microgrid connected to n number of loads, and the energy is coming from n number of sources, and those sources are intermittent, means you cannot guarantee the outcome of each and every energy resources at a given time. Certainly, the customers behaving randomly. So, the energy at each and every bus being injected is keep on varying, the loads are keep on varying. So, at a given time the load and generation need to be balanced, and that balance is possible efficiently, optimally to exercise your local energy sources, and it could be a grid interfaced or maybe an islanded operation. Different control schemes are evolved, but just let us overview of the control mechanism what we have learned in last two lectures. Appropriate controls should be employed depending on the system parameters and the prevalent operating conditions. A hierarchical control strategy provides better load sharing with improved frequency and voltage regulation. Unbalanced microgrid system employing nonlinear loads can achieve accurate load sharing by appropriate control strategy such as high frequency signal injection, harmonic current sharing, and addition of proper and adaptive output impedance between DAR and main grid bus. Communication less control strategies such as droop control are independent of the geographical distance between the DGs and its load. However, they are less reliable due to the absence of interaction between the distributed generators. Decentralized control techniques are gaining popularity due to reduced risk of single point failure of control, unlike centralized control strategy with cooperative and intelligent control and multi-agent based methods. These two references are very frequently used in today's lecture. So, I request all of you to please refer these two references thoroughly. Thank you.